In section 1.1, we just give a little overview of what the class is about, what differential equations are. We talk a little bit about some things, some ways of classifying differential equations. So we'll talk about a little bit of terminology and then we'll get into some examples. So a differential equation is just some equation that has a derivative in it, has a differential in it. So for example, if we have y prime plus 3y equals 7x, that's a differential equation because we have a derivative in it. We could have something written in the form dy dt plus 3t equals 7. We have a differential equation because our equation has a differential in it. And a lot of things in life, a lot of equations involve differentials because what is a derivative? A derivative refers to a rate of change. So a lot of times when we're looking at systems, we're looking at their rates of change. How fast are certain quantities changing inside the system? And we can relate those. So anytime we have equations that relate rates of changes, then we're dealing with differential equations. Now we need to talk about in terms of our variables, which is the independent, which is the dependent variable. So when we look at a function, for example, something like this, typically our input variable is our independent variable. Our output variable is our dependent variable. So if we were to make a table of this equation, we would randomly pick a number for x independent of what the other one is, and then depending on what we put in for x, that would give us a certain y. So the value of y depends on what we put in for x. So this is the independent and this is dependent. In terms of things that are differential, when we have imagine if we were to take the derivative of this function, typically we would be taking the derivative of this with respect to x. So whatever variable we're using to take the derivative with, that's our independent variable, and the other one is dependent. So if y prime is a derivative with respect to x, then dx is the independent, or x the independent, and y is the dependent. In this second one, we're taking the derivative with respect to t. So t is the independent variable. Y is the dependent variable. So another thing we have to keep in mind, sometimes we refer to things such as coefficients. So a coefficient is a number out front, or in some cases, in differential equations, a coefficient could have a variable. So if our base variable here is y, what's in front of it, that is our coefficient. So here we have a coefficient of 3, here we have a coefficient of 7. If let's say we put another variable in front here, let's say we had a t squared in front of this derivative, then we have a coefficient here, a coefficient here, and then a constant on the other side. So our coefficient is whatever is in front of our variables, or in front of our variable, our differentials. Something else we want to keep in mind is the difference between ordinary differentials, or ordinary differential equations, and partials, or partial differential equations. In this class, we're going to be dealing almost exclusively with ordinary differential equations. And an ordinary differential equation is a differential equation that only has your regular differentials in it. So dy dt plus 7y equals 4t. we don't have a partial derivative in this. Sometimes the dy's and dt's are separated. We might have 3 dy plus 4 dt equals 5. Still, in that equation, it has differentials, but they're ordinary differentials. So both of these we refer to as ODEs, or ordinary differential equations. Have one that has partials in it, such as the partial of x with respect to t plus t equals 7. If we have a partial derivative in it, then this is a PDE, a partial differential equation. And again, we're not really going to be dealing hardly with partial differential equations. We're just going to be dealing with ODEs. And the study of differential equations is really wide. We're only going to be able to get into a small portion of it. We're only going to be able to do differential equations up to a certain order and of certain types. If we get past certain types, get into other categories, then it's going to get beyond the scope of what we're going to have time to cover in this class. So we're just going to cover, if we look at the whole set of differential equations, we're going to just cover kind of just a little niche of that. A significant niche, but it's going to be the more standard, more ordinary types. The other thing we want to classify in section 1 is linearity. What's the difference between a linear and a nonlinear differential equation? So when we think of regular equations, something that's linear has our variables to the first power. If it has x, y's, and z's, each of those is to the first power. While on the other hand, if we have any of our variables to more than the first power or to any other power, could even be a radical, then they would be nonlinear. Well, a similar convention applies to differential equations. Not exactly the same, but if we look through our book and look at definitions, so in order to classify these, we do have to have the good understanding of independent and dependent variables. So they write out, we have some coefficient and then some derivative of y with respect to x, and then we have the next lower derivative of y with respect to x, and so forth. As long as these coefficients are in terms of the independent variable, as long as these all deal with the independent variable, in this case x, then this is said to be linear. But if it has the dependent variable y in them, then it's not linear. And it could be that the coefficient could have various powers of x, various powers of our independent variable, as long as it doesn't have our dependent variable in there. So let's go through and look at some examples. So let's take a look at some examples. Let's begin by looking at this one. So I'm going to list the dependent and independent variables. So the independent variable in the first one is x. The dependent variable is y. So we cannot have our dependent variable to a power other than 1. If it's going to be linear, our dependent variable has to be to the first power, and our coefficients have to be just x's. Notice here, our dependent variable is raised to the third power. So if we have a dependent variable to any power other than 1, then this is nonlinear. Just like in y equals x cubed, that's nonlinear because we have something to the third power. Same idea here. A little bit more complicated because here it does depend on which variable it is. Also remember that this notation does not mean that we have something raised to a power. This just tells us which derivative we're referring to. We're referring to the second derivative. All right, so let's take a look at the next one. So the next one, our independent variable is t. So dependent variable x, so we can't have, if we have a differential, we can't have a coefficient of x. If we have x to the first power, we can't have a coefficient of x, or we can't have x to any other higher power, in other words. This actually is linear for that reason. It doesn't matter about our independent variable, what powers we have in it. It only matters that in our dependent variable, x, whether it's a derivative, a second derivative, a third derivative, whether it's x by itself, as long as the derivatives or the variable of our dependent variable are linear, occur to the first power, and don't have a coefficient of that dependent variable, then that is linear. Third one, our dependent variable is y, our independent variable is x. So do we have a coefficient of y? And yes, we do. We have a derivative here and a coefficient of y in the same term. If this y was over here by itself and not in the same term as the differential, then that would be okay. But since they occur in the same term, think about we have a y here, something with respect to y, and a y here. We have more than one y, so essentially we have a y squared or y to some other power. So that makes it nonlinear. So if we have a y and a differential of y in the same term, not linear. Okay, if we look here, we don't have a coefficient per se, but we have a differential of y, and it's to the more than the first power. This 2 here doesn't mean that it's the second derivative. It means that we have this differential times itself. Well, we have two differentials with the same with the same dependent variable in the same term. If it's more than one, then that's nonlinear. So essentially, to be linear, our differential, our dependent variable, has to be to the first power. Any coefficients have to be of the independent variable.